All right, today is the class. I'm going to put this on today. No, I'm not. Okay, so we are reviewing this topic. These are just complex numbers, using imaginary numbers as well. Complex is actually when we have a real and an imaginary, but we'll break all that down. This is a review from 1.3.1. The one thing we need to remember is no negative roots are allowed. So you can't have a negative root, and why is that? So let's think about, what is the square root of 4? 2. 2. You have to have a positive 2 times a positive 2. Right? So what would the square root of a negative 4 have to be? To get a negative number, you need what? You need a negative and you need a positive. So really the square root of a negative number doesn't work out because the square root tells us that we need that same number multiplied together to give us what's in the root. So we can't have a root negative 4 because you need a negative 2 and a positive 2. And that's not proper. That's incorrect. So instead, what was devised? They came to that cul-de-sac of mathematics and decided to just reinvent. And instead, they decided to create imaginary numbers. And these imaginary numbers define the square root of negative 1. So that negative under the root, it defines it as I. Imaginary, I. Remember this. The thing with these imaginary numbers is they have this interesting cycle that happens. So if I take I, which is equal to the square root of negative 1, I better pen. No. So I take I, it's the square root of negative 1. If I square it, if I take I and I decide, I'm going to square it. Nah. Sorry, I need a better pen. And we're back. All right. Where was I? So if then we are looking at I squared, we're going to take the square root of negative 1, which was I, and we're just going to square it, right? Now, what kind of operations, what could I call these operations? They're what? The square root and squaring a number. What kind of operations are those? It's similar to multiplication and division. What kind of operations are those in relation to each other? Inverses, right? So when we apply the inverse, it cancels out both of those operations. So I cancel those out. So I know that the square root of, I squared is negative 1. We could work out all these definitions for I, which is I to the first, I squared, I to the third, I to the fourth. If you do so, you will start to see that this pattern continues the cycle. So if I look at that idea and I write down a few of these, I to the fifth, I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th. When we get to I to the fifth, just like in the cycling through of first, second, third, fourth exponent, when I get to the next exponent, I go back to the front, the top, and that is an equivalent I value. So I to the fifth is going to be square root of negative 1. I to the sixth is negative 1. I to the seventh is negative I. I to the eighth is 1. Who can tell me what they think I to the ninth is going to be? I to the ninth? Square root of negative 1. I to the 10th?
Negative 1.
Negative 1. Okay. So the next thing we have to overcome is, what if we had to find I to the 103rd? We could go through this process, right? It'd be really boring. We'd make all these numbers, I'd get all the way down, finally get to I to the 103rd, then I'd find my answer. But since we know that they cycle through, this is the approach we're going to use. We're going to take the exponent of our I value, divide by 4. The remainder is our new exponent. Not just new, it's the equivalent. New and equivalent. All right. So I'm going to go ahead and try to do this I to the 103rd. I'm going to take 103. I'm going to divide it by 4. I know that 25 goes into 100, so let's go ahead and jump there. 3. I found that it's a remainder of 3. because it's a remainder of 3, I know that I to the 103rd is identical and equivalent to I to the 3rd power. Then we just reference our 4 defining exponent values for I. And what would I to the 3rd be based on those that we already figured? Negative I. You see? So knowing that the pattern always goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Since these are always going to be the identical cycle that we go through, we can use division, dividing by 4 and finding the remainder as our way to find the equivalent. Okay. So I'd like for you, on your own, and then check with the neighbor, go ahead and find I to the 8th. Go ahead and find I to the 8th. So take 8, divide it by 4, double check with your neighbor. 1.
No remainder. So 0 is equal to I to 0.
Just count it out. If anyone wants to take I would be
Wait, so for 8, for I
You can do it that way, Lawrence, at this point. But when you get like I to the 52nd, that's going to take too long.
because when I did divide it by 4, I got I.
Well, it's 2, right? But what's the remainder? Remainder is 0. So I to the 0, anything to the 0. All right, let's bring it back. Bring it back. Let's look at this. I to the 8th power. I heard Lawrence talking it through. He was thinking, well, since it's 8, I can kind of just count it out. I know this would be I to the 5th, I to the 6th, I to the 7th, I to the 8th. Okay, that's totally valid. When the numbers are low, we can do that. But what if I said, what's I to the 271st? That's going to take too long. So don't do it then. We want to practice this division trick here, this tool, even on small numbers to start. So I take 8, I divide it by 4, I get 2, but 2 is not the remainder. 2 is the quotient, it's the answer. So when I work this out, remember 0, remainder 0 is what the remainder is. So that tells me that I to the 8th is equivalent to I to the 0 power. Anything to the 0 power? 1. Okay. All right, I want to make this trickier. Sorry if you already did it. Not really. How about I to the 17th? Go ahead and try that one. It's an extra 10 seconds of work. All right, for this one, I'll give you about 15 seconds. So divide by 4, find the remainder. Boom. Maybe you can do it in your head already. Use the Rice Krispie machine? I would have Krispie machine. You make Rice Krispie. Yeah. That's gross. Yuck. Alright, let's bring it back. Bring it back. We're doing I to the 17th. I to the 17th, what's the strategy? Walk me through it. Divide by 4. I take 17. Divide by 4. And what can we do? 4, 16, minus 1. Remainder is 1. So I know I to the 17th is I to the 1st, which is?
I confused myself.
Did you say square root of pi?
No, I didn't say square root of pi. I want the square root of pi. I would just agree with pi.
All right, I think I'm going to do I to the 10th with you right here. I to the 10th. Take 10. I to the 10th, we divided by 4, 2, 8, 2. Remainder, 2, which is negative 1, because We have a remainder of 2. We have a remainder of 2. So it's I to the second power, which is that -1 value. But these are equivalent. These two things are equivalent because it always cycles. Okay. How do we feel about this? We've seen it before. Thumbs up, sideways, down. What do you think? Yeah. Embarrassed to even put your thumb up because it's too easy. Okay. That's fine. You're all. We know nothing. We do not. We know nothing.
How did we solve this problem?
How do we?
Did you do it? Did you do it right?
True. That's
Are
true.
you sure? Yeah.
How do you know? All right, let's go ahead and jot this real quick to the squiggly line right here. This is just complex numbers. Actually, I'm going to go ahead and elaborate as you're jotting it down because it's such a small amount here. Complex numbers involve a real and imaginary component. Real and imaginary. We know that it's imaginary because it has an I value in it. That's an imaginary number. We can only combine like terms. So, just like an iPhone, if I have an iFriend, what do I have?
And I
You have an imaginary friend. We all had them when we were growing up. But if you're hanging out with your friends, and you're like, oh man, Casper said something funny yesterday. He was. You cannot. Daniel knows from personal experience. It's cool. So you don't want to mix up talking about your imaginary friends and your real friends. That's just weird. You cannot combine. All right. You cannot combine real and imaginary components. All right, Yanni in the back. Come here. So real are the whole numbers in this case. The imaginary has an I component to it. So if I'm looking at this, only combining like terms, this is adding these two expressions together, which really, since it's adding, I can just look at it pretty directly as a bunch of terms here. Which terms can I combine? Which one are our real friends? 7. We have 7 real friends. How many imaginary friends do we have? We had 3 imaginary friends, but they left. That's horrible.
In your imaginary person?
Yeah. It's a joke. I know, it's hard to resist. Don't overthink it. All right. Let's look at the second part. What is different with this second aspect here that I need to pay attention to? What looks different? There's no square roots. I just heard square root. There's no square root. William, you know.
There's an exponent.
There's an exponent. I to the 4th power, right? We got to deal with that. What else? There's a negative, so this is negative applying to the whole expression. So what we need to deal with is the things we need to are here. And we got to distribute that. So I say let's deal with this part first. It's a definition. It's one of our defining I values. So I to the 4th is 1 minus 1. I'm going to distribute this one. So we get -10. And we get -3i. Well, let's add up together all our real friends now. Too far. 6 minus 1, 5 minus 10. -5 minus 3i. So we've lost 5 real friends and 3 imaginary friends. Maybe they moved. Maybe they moved out of state. It's not nothing to get. That's true. All right, we're gonna tell all of our real friends to subscribe, and then we're gonna tell our imaginary friends to subscribe. All right. All right. Let's do a real subscribe on 3. Real subscribe. 1, 2, 3.
Subscribe.
Let's try it again. Real subscribe on 3. 1, 2, 3.
Subscribe. Okay. Not fake subscribe.
Imaginary subscribe on 3. 1, 2, 3.
Imaginary subscribe.
Don't imaginary subscribe. You want your Kit Kat 79th.